Okay, and here comes the second distinct talk by the Professor Evangeline Young. Ivan is currently the chair of the CSE department of the CUHK in Hong Kong. Yeah, it's very much higher salary than I believe because of this is a special session and all speakers all belong as scholars in our area. So probably don't need to go into detail for all this introduction. Yeah, Ivan is the IGP fellow, and also I believe Ivan has received the most champions in our EDA contest. Either you or me. I believe it's you. Yeah. And Ivan already has published many influential papers which already changed our EDA landscape. Yeah. So that's welcome, Ivan.
Thank you very much, Young, for the warm introduction. And you are always welcome to join CUHK. Okay, so I'm very honored to be included in this tribute section. So this section is to pay tribute to Martin. And so a few months ago, when I was asked about the title of the talk, then I thought about it a few days, and then I think of this one. So one thing is that is because Martin is a pioneer in doing GPU acceleration of EDA. Okay, one thing. The other thing is, I do think Martin is the person accelerating EDA from 1 to n. Okay? So that's why I choose this title as my talk. I did some research about the students of Martin. So you can see here, those on the left are from UT Austin, and those from the right are from UIUC. And up to now, Martin graduated 54 PhD students. And one thing is, this list is still growing because after Martin joined us 5 years ago, he co-supervised the PhD student with me and other colleagues of the department. So the first batch of co-supervised students is going to graduate this summer.
Parallel processing. Oh, there's a mission. Yes, good. Wow.
You have a real good memory. Besides Einstein, you also So, well, I'm very lucky to be the 18th student of Martin. So when I prepare this talk, I try to recollect some of my memories about Martin, and there's a little story to share with you. So in that year when I was applying for graduate school in the US, Martin was the admission coordinator of the Department of Computer Science. So he was the person sending me the admission offer. And a few weeks later, he was also the person sending me about the scholarship. So at that time, I felt so thankful. And I wrote to Martin, I say, Professor Wong, you look like a Santa Claus to me. I don't know whether Martin, you remember this. Probably not, right?
That wasn't that fact.
Okay. And then after 25 years, Martin joined us, CHK, and once again, I got the same feeling because Martin did a lot of good things to me and to all the colleagues in the faculty. So he brought in a lot of these resources and also helped many colleagues to advance in their career path and did a lot of good things. So I confirm that Martin is indeed the Santa Claus. He's very kind and he's very helpful in all the situations. So I'm really lucky to be his student. And then here I draw the academia and you can see Martin's students and Martin's students' students. And one thing I want you to pay attention is that this tree is still growing. So here I put n as a variable, so nobody know what is number. So besides this, actually Martin is indeed a pioneer in doing GPU acceleration of EDA. The first work of Martin on this is back to 2010. It's about GPU implementation of reverse search. So this work received a lot of attention, and the citation is more than 300. So after that, Martin did a lot of other works on GPU acceleration, including power grid analysis, area image simulation, and then routing and placement, and recently multi-synthesis logic optimization. Okay. So in this talk, I'm going to walk you through some of the previous works by Martin. So this is the first work. So this one appeared in back 2010. It's done by Martin and one of his female student, Lori Jun. So this one is GPU acceleration of reverse search. So we all know that reverse search is very important. So it doesn't just appear in EDA, it also appears in other areas. And we all know that on CPU, when we do reverse search, we will make use of Q, right? We enqueue and dequeue. And then so we started from a source, then we visit the second level frontier, third level frontier, so on and so forth, until we visit all the vertices in the graph. Okay? So that's reverse search. So we want to do parallelization, so we need to think about how. Because if we still maintain one queue, okay, even if we have many processes, but everybody need to write to the end of the same queue, then it will be atomic and sequential. All right. So in that work, they will propose this hierarchical queue management. So some part of the queue will be kept in the global memory, which is called the G frontier, and then some part of the memory, some part of the queue is kept in the shared memory, which is much faster to access. So they are the block frontier and the walk frontier. And then they also carefully synchronize their GPU thread so that they can make sure there are at least 4 threads accessing the walk frontier at the same time without conflict. Okay. So they also do careful synchronization to make sure the nodes will be visited in a reverse search manner, so level by level. So by doing that, they can achieve a speed up of 2 times to 5.6 times. So remember that that's 25 years ago. So the GPU at that time is not as powerful as today. So getting a speed up of 2 to 5.6 times is very impressive, 25 years ago. And after that, Martin did a lot other GPU acceleration work, like timing analysis, aerial image simulation, and this interval tree computation. And then in year 2019, Martin got a contract from DARPA, which is to accelerate the EDA tool, some of the fundamental EDA algorithm, by using parallelism on heterogeneous systems. So you know, as circuit becoming more complex, some of the EDA tools run really slow. So the aim of the project is to make use of parallelism on heterogeneous system to speed up those fundamental EDA algorithms. So what Martin and his students thinking of is to build a high-level programming system to help people to do this parallelization. So, but this is not easy. There are many challenges, like we need to have transparency for the user, and also we want to have sustainability. You know, many things are changing. The software is changing, and the hardware are changing, how you can be sustainable. So after that, Martin and his student Zheng Wei created this task flow. So this task flow is a task graph implementation system. So this allows user to, in a simple way, to schedule their task on a heterogeneous system. So you can see from this simple example, how a user just write less than 20 lines, maybe just 10 lines, to schedule their task in Power. And one special thing about this task graph is that they also allow the task to return some value to the scheduler, so that the scheduler can invoke some other selected task, so that they can create more complex control flow instead of just a DAG-based control flow. So nowadays, task flow is very popular and is being used by more than 1,000 projects. Thanks for the good work started by Martin and his student. And after this one, I think many of us remember Martin also did a lot of GPU acceleration on timing analysis, right? Back to 2019, there's already a piece of work from Martin's group on accelerating the path-based timing analysis using MapReduce operation on GPU. And this work is the most updated one by Martin and his PhD student Huan Nan. Huan Nan is the second last PhD student from UIUC, supervised by Martin. And this work is using GPU to accelerate this path-based timing analysis. Okay. So we all know that one of the most difficult things to do for path-based timing analysis is to generate the path. So in this work, they leverage the parallelism of GPU to generate the path and to propagate the timing information through the path. And you can see the blue blocks are running on GPU and the white blocks are on CPU. So the CPU will be used to integrate the information, update the SK graph, and then they will regenerate the graph. By iterating a number of times, it will become more and more accurate. So they invent this data structure called the shortest path forest. So this data structure consists of a set of trees, and then you can see that these trees, they do not duplicate to avoid wasting of memory. So these trees are constructed by GPU in parallel. Okay. And then after they construct the tree, they will propagate the timing information across the tree. So this is also done in parallel on GPU by some level-wise parallelism. So they will do a level by level parallel computation to propagate the timing information. So they have a technique called the look-ahead level allocation, which is to pre-compute the position of the memory when they are going to write to the next level, so as to make sure when they write, they do not conflict. Okay? So that can ensure a higher level of parallelism. Okay. All right, so they compare with a open timer on a CPU with 40 threads. They can get a speed up from 25 times to 46 times, which is very amazing. Okay, so these are some of the previous works by Martin and his student on GPU acceleration, where Martin was in UT Austin and UIUC. And after Martin joined us 5 years ago, we did some more GPU acceleration. So one of the reasons is we can all see that GPU nowadays are very powerful, right? But we don't know why many of the commercial tools are still running on CPU. And there's really a need to push to use more GPU. So we can see speed up of huge scale. So why not using more GPU for those EDA tools? So that's why we try to explore. And recently we did works on physical synthesis and also logic synthesis. Okay, so let me tell you more about those works. So one is about physical synthesis, placement, and routing. So this one is about GPU accelerated placement. So we have this X plate, so which is similar to E plates on CPU, and also similar to Dream plates on GPU. But for X plates, we have a cleaner implementation, more sharing of the operators. So it can be like 2 to 3 times faster than Dream plates. And recently, we also incorporate this GPU accelerated router inside the placer. Okay? So we can do detailed routability driven and very fast. Okay? So this is our X-Place R. So it consists of two engines, the placement engine and the routing engine. And here, so you can see, so some of the result here. So this is X-Place R, and then this is the placement time. So you can see on average, the time is just 41 seconds, including all the routability-driven estimation and the placement. And this is the ISPD 2015 data set, detailed routability-driven placement contest. And then we run the commercial tool and check the VLC. So we can compare without the global routing. So this one is X-Place without R. Okay. So you can see the average time is 14 seconds. So just 20 to 30 seconds more, then we can do routability driven. And so we can also compare with CPU. So this one is a very high quality detailed routability driven placer, NPU place for detailed routing. So you can see comparing with on CPU, the speed up is 43.82 times. Okay. All right. So this X-Place R is on our GitHub. It's open source, so you can check it out. So the next thing is about routing. So I want to talk about this routing because this very first work on maze routing is a collaboration with Martin. So this is about GPU acceleration of maze routing. And after maze routing, we also recently did more GPU acceleration for panel routing. Okay? So some of them are for the contest tomorrow. So let's talk about this maze routing. So this maze routing appeared in 2022, TCAT. This is to accelerate maze routing. So you know that maze routing is very much used in different routers, right? But on the other hand, it is very slow because it's doing a breadth search on a regular graph. So we want to see whether we can accelerate this. So in order to solve this problem on GPU effectively, instead of doing breadth search, we try to replace by a sequence of sweep operation. Okay, so horizontal sweep, vertical sweep, horizontal sweep, so on and so forth. And finally, we will achieve the same result of maze routing. But the good thing about this sweeping operation is that it can be formulated as a prefix sum operation. A prefix sum operation. So we know that prefix sum can be computed very effectively on GPU. So at the end, we can get a speed up like 50 to 100 times for the this maze routing. And very recently, we also do this GPU acceleration of pattern routing. So here, I tell you some of the things that we did trying to increase the parallelism of routing. So here is one of the technique. So you know, for routing, in many cases, people, when they talk about parallelism, what they will do is to try to divide the net into batches. So that the net in the same batch can be routed at the same time. Okay. So what people will do is to look at the bounding box, okay? And then if they overlap, then these two nets cannot be routed at the same time. They will put it on different batch. Okay? So here, if we consider L-shaped routing and also consider some of the pins inside the net, we can have smaller bounding box. So for example, these two nets, they actually do not overlap. Okay? So they can be routed at the same time. They can be put in the same batch. Okay? So in this way, we can increase the parallelism. And we can also do some other techniques, like this one, for example, this net. If we look at the bounding box, it's inside the big net, so they cannot be routed at the same time. But if we choose the grid lines right, so choose a coarser grid graph for the big net, a finer grid graph for the small net, then the two nets can be routed at the same time. So they can be put in the same batch. So in this way, we can increase a lot of parallelism. So we also have this level-wise parallelism for DAG-based pattern routing. So I would leave this to tomorrow. So this is, so rather than drilling into the detail, okay. So the last thing I want to tell you about our collaboration with Martin is about logic synthesis. Okay, this is the last thing I want to mention here. So, it's very exciting to do this. We used to do physical design a lot, and recently we started doing some logic synthesis. So this all starts with, again, a contest. So there's a GPU accelerated contest on rewrite. And then this is also the first work we cooperate with Martin on this logic synthesis GPU acceleration. So we try to parallelize this rewrite operation. And at the end, we get a speed up of 2.91 times. So we are very excited about this. And after that, we do a lot more other operators, like refactoring, rebalance, resynthesis, technology mapping, and K-resubstitution. And inside the bracket, you can see is the speed up that we can achieve. And all these open source on our GitHub. And one thing I want to mention here is that I know many of us are still using CPU and GPU at the same time. So here we provide two modes of compilation. So you can compile to GPU standalone mode. You can also compile to ABC patch mode so that you can call some ABC CPU version operator or our GPU version operator. And then we have the gget and gput, two operations that you can convert between the two data structure. Okay, so you can check out the website and try it. So some of the background here. So we are doing ARG resynthesis. So ARG stands for an inverted graph. So for example, this resynthesis flow consists of a number of operators like balancing, rewrite, refactoring. So one difficult part about this type of work is that if we just speed up, for example, rewrite, okay, without speeding up other part, then the overall speed up will be just 2 times, 3 times, okay? So we need to work on every one of them. If we want to say, I want to have 50 times speed up, okay? I need to have 50 times speed up for everyone, okay? So that's why after doing this lawful write, this rewrite, we try to work on refactoring and balancing, okay? So, so here I quickly go through this. So this is refactoring. So refactoring basically is to resynthesize the circuit, okay, the ARG. And what it's doing on CPU is that they will visit the node one by one. Okay. When it arrives at a node, they will identify a cone, okay? And then next they will see whether the cone can be replaced by a smaller one, okay? By like algebraic factoring. So if it can be replaced by a smaller one, they will replace it. And then they will proceed to the next vertex. Okay? So this is the way it's done on CPU. So you can imagine they are changing the AIG on the fly. So how we can do it on GPU in parallel? So we need to think differently in order to solve this problem to achieve a high level of parallelism. So instead of following this flow, rather we split the whole process into 3 stages. So the first stage is everybody identify the cone. Okay, every node identify the cone. Okay, at the same time. So this is the first stage. And then the second stage is everybody do resynthesis. Okay, so this could be done quite straightforwardly for the second step. And then the last step is to combine them. So this is usually the problem you will beat if you want to do things in parallel. So, so at the end, we try to do this parallelization, and we are successful to parallelize it. And we definitely need to use some data structure like hash table to avoid duplicated vertex in the circuit. And we also parallelize this balancing. So I think I better skip this, okay? Although the problem itself is very interesting. So here I will just jump to the result and tell you that, for example, for balancing, by doing this level-wise parallelism, we can have a speed of like 14.8 times. And then the refactoring, because we do this 3 stage, is a high parallelism, so not only level-wise, but also node-wise parallelism, then we can achieve like 42.7 times acceleration. And then we put them all together, the resync 2, with the rewrite, rebalancing, and refactoring, the speed up is close to 46 times. Okay. And very recently, we do some more work on technology mapping, also for ABC, and the speed up is 120 times. So it's all very exciting result to us. So we want to do some work and do some bigger problem, make good use of the parallelism that we are provided with. So that's all I want to share with you about the technical work and also the collaboration with Martin. So after I tell you all this, I think we all know how to fill in this blank. Okay, so what I want to say is Martin is indeed the person accelerating EDA from 1 to n. Not only technically contributing in research, but also nurturing a lot of students, and they all do research in EDA. So thank you very much, and also congratulations to Martin.
Thank you. Thanks, Ivan, for the very inspiring history. You finally get rid of Martin's control now. So any question from the audience? That I would like to cue the payment for Martin's work and the UIUC. Please keep your answer very brief. Okay. Yeah.
Sure. Yeah. So thanks for giving me this chance to talk about Martin's work. So I know Martin for a long time before I joined the UIUC in 2005. Right. So actually, the reason I could join UIUC is because of him. Right? So that's just a very honest assessment. So then actually our office is side by side, right? And then Martin, even he becomes a provost of famous Hong Kong University. He still visits us, and we sit down, we have coffee, we chat, and he's always been an inspiration. He has been my mentor, and we co-advise 3 PhD students. So that's why I know. Right. And I have learned a lot from Martin. Right? So the systematic approach to a problem, and when I think about Martin, I feel he's like a mathematician, right? And a very wise person, and a professor, and an EDA researcher all in one, right? So one side fits all, and it's almost too good to be true, right? So so it's no surprising, right? So he has made so much impact, and even he left UIUC, his impact is still ongoing, right? We still benefit from a lot of programs like the DJUI, right? So there is an international campus of UIUC in Zhejiang University. That was because of his effort, right? So that program is still ongoing, right? And basically, I'm trying to follow your step. Okay, thank you very much.
Thank you very much.
Thanks, Ivan and Dermin. Yeah, very touching.